In this video, Electrostatics Part 6, we will be studying the applications of Gauss Theorem. Let's recall what is Gauss Theorem. The Gauss Theorem states that the surface integral of electric field or electric flux linked with a closed surface is 1 over epsilon naught times the total charge inside the surface. For example, if we have this closed surface S and these are the various charges present inside the surface, then mathematically flux phi E is equal to integral of E dot ds over closed surface S is 1 over epsilon naught multiplied by the charge enclosed in the surface, where Q is the algebraic sum of the charges inside S. The applications to be studied are the electric field intensity due to an infinitely long line of charge, due to infinitely large flat sheet of charge, and due to a uniformly charged spherical shell. Now, before we proceed for the derivation of the expression, there is a regular pattern which will help you derive the three expressions. These are the various steps involved in all the three derivations. Step A, choose a suitable Gaussian surface. It should be closed and should be suitable in different situations. Then we calculate flux, electric flux phi E as surface integral of E dot ds over the Gaussian surface chosen in step 1. Next we calculate the electric flux by Gauss theorem, that is 1 over epsilon naught into the charge enclosed inside the Gaussian surface. We get two expressions for electric flux from step B and step C. Here we equate the values of phi E from the two steps involved, and that will give us expression for the electric field. And lastly, after getting the expression, we will study the expression carefully and see the factors on which the electric field intensity depends in different cases, and the subsequent graphs which are used to express the dependence on the various factors. Now, coming to first application, electric field intensity due to infinitely long line of charge with linear charge density lambda coulomb per meter. Here this is an infinitely long line of charge. Let's consider that the charge is positive and the charge density is lambda coulomb per meter. P is a point at a distance r from the line where we want to find out the field intensity. For the purpose, we consider a cylindrical Gaussian surface of length L and radius r. L is any arbitrary length, and the given line of charge as the axis of the Gaussian surface. Now, as stated in the steps earlier, we will calculate flux in two different ways. The electric flux phi A linked with this cylindrical Gaussian surface can be written as integral E dot ds cylindrical surface, here curved surface, plus these circular ends. Curved surface plus integral E ds circular ends. Here on this curved surface, if you take an elementary area ds, and this is normal drawn to the elementary area, the field is directed away from positive charge. So electric field is upward and the normal is also upward. So angle between field vector and the area vector is 0 degree for the curved surface. However, if you take an elementary area here, the normal is horizontal and the electric field is vertically upward because field will be away from positive charge again. So the angle between field vector and area vector is 90 degree for this circular end as well as this circular end. So we can rewrite this expression as E ds cos 0 for curved surface and E ds cos 90 for the circular ends. Therefore, phi E, the electric flux, is E integral ds because E is uniform throughout the curved surface. The E, you can take it out of the integral. E integral ds over entire curved surface plus 0 because cos 90 is 0 for the circular ends. That is, here in this case the circular ends do not contribute to the flux. The total area of the curved surface is 2 pi RL. So the flux phi E is E into 2 pi RL. Let's write this as expression 1. Now if you apply Gauss theorem to this cylindrical Gaussian surface, we get flux is equal to 1 over epsilon naught charge inside S. This is the charge inside S over a length L with lambda coulomb per unit length. So total charge will be lambda into L. So the alternate expression for the flux by Gauss theorem is lambda L over epsilon naught. This we write as equation 2. Now if you compare equation 1 and 2, you get E into 2 pi RL equal to lambda L over epsilon naught, or if you cancel out L from the two sides, E is equal to lambda over 2 pi epsilon naught R. As you can see from this expression, E is directly proportional to lambda. Therefore, the graph between E and lambda is a straight line. Again, E is inversely proportional to R. Therefore, the graph between E and R will be hyperbolic. That is, as R increases, the electric field will decrease. Now for the second application, that is electric field intensity due to a large flat or plane sheet of charge with uniform surface charge density sigma coulomb per meter square. Let's consider this as the sheet with infinite expanse. That is why we show this zigzag ends, means it can be extended infinitely to either of the directions. P is a point at a distance r from the sheet where we want to find out the field intensity. Let's consider a cylindrical Gaussian surface with length 2r and a uniform area of cross section ds. Now here at this point, that is on circular end, the area vector is towards right along n cap, and the field is also towards right because it's away from positive charge. Therefore, you can write this at circular ends, E is parallel to n cap or E is parallel to the area vector. However, on curved surface, if this is a small element, then field will be towards right away from positive charge and area vector will be upwards along this n cap. So on curved surface, field is perpendicular to n cap or field is perpendicular to area vector. In case of circular ends, angle between field and normal to the surface is 0, and in this case it is 90 degree. Now as usual, we will find out the flux in two different ways, by integration and by Gauss theorem. First, by integration, flux phi E is integral E dot ds over entire surface S, cylindrical surface. This circle on the integral shows that it is a closed surface. This integral we can divide it into two parts, curved surface separately, circular ends separately. For the curved surface, we have theta equal to 90 degree. So we write E ds cos 90, and for circular ends theta is 0 degree. So this integral is written as E ds cos 0 over the circular ends. As cos 90 is 0, this expression will not make any contribution to the flux. This comes out to be 0, and here the entire area ds, total area ds for the circular ends will be ds plus ds. Since there are two surfaces, two circular ends, the total area will be 2ds. So flux is E into 2ds. Let's write it as expression number 1. Now by applying Gauss theorem, the electric flux is total charge inside the cylinder divided by epsilon naught. Now the charge inside the cylinder is on this shaded part of area ds. So the total charge is sigma ds over epsilon naught. This is equation number 2. Equating 1 and 2, we get E into 2ds, E into 2ds equal to sigma ds over epsilon naught. Here ds is common and can be dropped, which gives you E is equal to sigma over 2 epsilon naught. And at point P, field is towards right along the direction of vector r. So we can write it as r cap, E equal to sigma over 2 epsilon naught r cap. A careful study of this expression shows that E is directly proportional to sigma and E is independent of r. We don't have this r here in this expression. If you plot a graph between electric field intensity and sigma, you'll get a straight line. Here again, a graph between E and r is a straight line, however parallel to x-axis or the distance axis, because with the change in distance E, the electric field remains unchanged. For two large plane parallel charge sheets P and Q, let us suppose P has a charge density sigma 1 and Q has a charge density sigma 2, and further assume that sigma 1 is greater than sigma 2 greater than 0. That is, both the plates have positive charge density and P plate has a larger charge density. In this special case, we want to find out the field due to the two plates. The plates divide the entire space into three parts. Part 1 left of the plates, part 2 between the plates, and part 3 to the right of the plates. To find out field at point P1 and P2 and P3, let's see. For P1, the field due to plate P is towards left. E1 is towards left and its value is magnitude is sigma 1 over 2 epsilon naught. Similarly, field due to Q at P1 is sigma 2 over 2 epsilon naught, again towards left. Hence the two fields will be added. So at P1, EP1, field at P1 equal to E1 plus E2, or sigma 1 over 2 epsilon naught plus sigma 2 over 2 epsilon naught, both towards left, leading us to this expression minus sigma 1 plus sigma 2 over 2 epsilon naught along minus x direction, and that minus x direction is taken care of or is represented by this negative sign. So field at P1 is sigma 1 plus sigma 2 over 2 epsilon naught towards left. Similarly, at P3, the two fields, that is field due to plate P and due to Q, will be towards right. Again, they will be added up, which leads you to EP3 equal to E1 plus E2, that is plus sigma 1 plus sigma 2 over 2 epsilon naught in positive x direction, and hence this positive sign. At P2, that is point in region 2 between the plates, the field due to the plate P is towards right, E1 is towards right, E2 due to the plate Q is towards left. So these two fields E1 and E2 need to be subtracted. So at P2, EP2 is E1 plus E2 equal to sigma 1 over 2 epsilon naught, positive because it is in plus x direction, minus sigma 2 over 2 epsilon naught, negative because it is in minus x direction, leading you to the expression sigma 1 plus sigma 2 over 2 epsilon naught. So these are the expressions for field in the three regions. Now another special case, supposing this plate P has positive charge density and Q has an equal negative charge density, that is sigma 1 equal to minus sigma 2 equal to sigma, which means sigma 1 equal to sigma, sigma 1 equal to sigma, and sigma 2 equal to minus sigma, sigma 2 equal to minus sigma. Using these values here for region 1, 2 and 3, this expression becomes 0. So E1 is 0. Similarly E3 will be 0 and E2 will be sigma plus sigma over 2 epsilon naught, which means 2 sigma over 2 epsilon naught or sigma over epsilon naught. This such a special case, that is sigma 1 equal to minus sigma 2 equal to sigma, we get in case of parallel plate capacitor. Now here we can use this method in order to produce a uniform electric field in a certain region, that is inside the plates of a parallel plate capacitor. The field will remain uniform given by sigma over epsilon naught. The magnitude of the field in this special case can be represented by this diagram pictorially. Here to the left of the plates, field will be 0, between the plates it will be constant, and to the right of the plates again it will be 0. Now for electric field intensity due to a uniformly charged spherical shell, let's consider a shell of radius r, a thin shell of radius capital R with center O, having a uniform surface charge density sigma coulomb per meter square. As you can see, the field due to the shell will be radially outwards for every point which is symmetrically placed around the center, and it will be acting along the radius. Now for point P at a distance small r from center O, if you want to find out the field using Gauss theorem, we have to take a spherical Gaussian surface S with center O and radius R. This surface is shown by the dotted sphere. Flux phi E is integral E dot ds over this entire Gaussian surface equal to E ds cos 0, because for this elementary area field is radially outward and area vector is also radially outward. That gives you theta equal to 0 degree. So E integral ds, because E has same magnitude over all the points which lie on this sphere. So E can be taken out of the integral. The integral of ds is the entire area of the Gaussian surface, which is 4 pi r square. This, let's mark it as equation number 1. Again phi E, the flux, is also 1 over epsilon naught into charge inside S, that is charge inside this shell. The charge inside the spherical Gaussian surface is the total charge on the shell, which is surface charge density multiplied by area of the shell, that is 4 pi r square. So this is by using Gauss theorem, because now this charge sigma into 4 pi r square is the total charge on the shell, which we denote by Q. So flux is Q over epsilon naught and flux is E into 4 pi r square. The equation 1 and 2 imply E into 4 pi r square equal to Q over epsilon naught, or E equal to 1 over 4 pi epsilon naught Q over r square. This is for the points which are outside the shell, that is small r greater than or equal to capital R. The expression also leads us to the conclusion that field is proportional to total charge on the shell and is inversely proportional to r square for r greater than or equal to r. Another point which we can note here is this is also the expression for the electric field intensity due to a point charge at O. So for all points outside the shell, the field due to the shell behaves as if the entire charge on the shell is concentrated at point O, leading us to this expression. If we have points inside the shell, then flux, if you take a similar Gaussian surface as taken here, spherical Gaussian surface, the same argument as in the case 1 leads us to the flux equal to E into 4 pi r square. However, if you apply Gauss theorem, we don't have any charge inside this dotted spherical Gaussian surface. So flux phi E will be 0 by Gauss theorem. Comparing 1 and 2, you get E equal to 0 for r less than capital R. Hence, the field vanishes inside a charged spherical shell, whereas outside it behaves as if the entire charge is concentrated at O. Graphically, we can represent the variation in this way. Up to small r less than capital R, less than the radius of the shell, the field is 0, and on the surface it is maximum. For r capital equal to capital R, the field becomes maximum and thereafter varies inversely as square of the distance from the center. So this graph shows the variation of electric field intensity with distance from the center.